Hey everyone, welcome back to Talk Tensors. Today,
Yeah.
we're diving deep into robust representation consistency model via contrastive denoising.
Ooh.
It's a paper that's really making waves in machine learning. Are you ready to get technical?
I am absolutely. This paper tackles a problem that's been kind of haunting deep neural networks for a while now.
Oh yeah.
Their vulnerability to adversarial attacks.
Yeah, it's a bit unsettling to think that like a tiny little tweak to an image can completely throw off a model,
Yeah.
especially when you think about how these models are being used for,
Yeah.
things like facial recognition or self-driving cars.
Exactly. The consequences could be pretty serious.
Yeah.
And that's why researchers have been exploring different techniques like randomized smoothing.
Randomized smoothing. I
Yeah.
remember hearing about that. It's kind of like giving the model blurry glasses
Right?
so it doesn't get tricked by those tiny little adversarial tweaks, right?
That's a good way to put it.
Yeah.
It has its limitations, though. It often comes with a trade-off in terms of performance and computational cost.
So how does this paper address those limitations? I'm really intrigued by this whole diffusion model
Yeah.
angle.
Yeah.
It's not the first thing that comes to mind when you think about robustness.
It's pretty innovative, actually.
Yeah.
Traditionally, diffusion models were known for their generative capabilities,
Okay.
creating realistic images or text or you name it.
Right.
But this paper uses them for robust image classification.
Okay, now you have to break it down for me. How do diffusion models, which are all about adding and removing noise, how does that help with robustness?
Well, think about it this way. Previous diffusion-based methods would use a diffusion model to denoise a perturbed image, and then they would feed that denoised image to a separate classifier.
Okay.
It was a two-step process, and it wasn't very efficient.
So two models, two steps sounds computationally expensive.
Exactly.
Yeah.
And that's where this paper really shines through.
Okay.
The authors reframed the problem. Instead of focusing on perfectly denoising the image, they wanted to make sure that the model's predictions stayed consistent
Okay.
between the noisy input and the clean version.
Interesting.
And they did this all within a single model, which they call
Okay.
the Robust Representation Consistency Model, or RRCM.
RRCM, that's a mouthful.
It is.
But I see where you're going with this one model, one step.
Right.
That's a pretty big deal when it comes to efficiency.
It is.
So how does RRCM actually achieve this consistency?
Well, the magic is in how they leverage the diffusion process itself.
Okay.
Unlike traditional methods, RRCM exploits the inherent structure of the diffusion model's noise schedule.
Okay.
This schedule determines how noise is gradually added and removed from the image during training. By tapping into this structure, they found a way to boost the model's robustness
Wow.
without needing a separate denoising step.
So this structured noise schedule sounds like a real game changer.
It is.
Can you elaborate on why that is such a big deal?
Of course. So it's significant because it allows the model to learn a smoother, more consistent representation of the data. Imagine walking up a hill with lots of little bumps and dips versus walking up a smooth paved path.
Yeah.
The smooth path makes it easier to reach the top right.
Right.
Similarly, the structure noise schedule creates a smoother learning path for the model,
Okay.
making it less susceptible to the bumps and dips.
Gotcha. So it's like it can handle the noise better because it's already
Exactly
those variations.
So you've seen it all?
Yeah. Okay, so tell me more about this two-stage RRCM process.
Okay, so in the first stage, which is pre-training,
Uh,
the model learns to align the representations of noisy and clean images along that smooth diffusion trajectory we talked about. It uses contrastive learning for this.
Contrastive learning.
Yeah.
Hold on. Can you explain contrastive learning a bit more for me?
Sure.
It sounds important, but I'm a little fuzzy on it.
Imagine you're showing the model pairs of images,
Okay.
one clean and one noisy.
Contrastive learning encourages the model to create representations where the clean and noisy versions are close together,
Okay.
but representations of different images are far apart.
Interesting.
This grouping by similarity helps the model see through the noise
Okay.
and recognize that the underlying image is still the same regardless of the added noise.
So during pre-training, the model is learning to see past the noise by understanding that the clean and the noisy versions are fundamentally similar.
Exactly.
Okay, what happens in the second stage?
The second stage is fine-tuning.
Okay.
Here, the model is further trained to accurately classify these noisy images while ensuring its predictions stay consistent with the clean versions.
Okay.
So it's learning to classify accurately and be robust to noise
At the same time.
all at the same time.
This is impressive.
And this happens in what's called the latent space.
The latent space? What is that?
You can think of it as the model's internal representation
Okay.
of the image data.
It's like the model's workshop, where it manipulates and processes information to make sense of the images.
So it's like behind the scenes, this is where all the magic is happening.
Exactly.
Okay, but before we get to the results, there's one term that you mentioned earlier that I wanted to touch on.
Okay.
The EMA schedule.
Ah, yes. The EMA schedule, or exponential moving average schedule,
Okay.
is a technique used to stabilize the training process,
Okay.
especially when dealing with complex models like RRCM.
Hmm.
It helps smooth out the updates to the model's parameters during training,
Gotcha.
preventing sudden jumps that could destabilize learning.
Okay.
Think of it like a shock absorber for the model,
Okay.
ensuring a smoother ride towards robust performance.
That makes sense.
Okay.
So RRCM cleverly leverages the diffusion process, uses contrastive learning
Right.
to learn robust representation, and employs this EMA schedule for stability.
Yes,
It sounds like a really solid approach.
it is.
But how well does it actually perform?
Well, that's what we'll dive into next. The
Okay.
results are quite impressive.
All right, let's hear it.
So they tested it on two popular data sets,
Yeah.
ImageNet and CFAR10,
Okay.
which are kind of like the proving grounds for image classification models.
Okay, so these are data sets that a lot of researchers use.
Right.
Which means we can directly compare RRCM's performance to other approaches.
Exactly. And the results speak for themselves on ImageNet.
Yeah.
RRCM outperformed existing diffusion-based methods by an average of 5.3%.
5.3%, that's a significant jump.
It is.
What does certified accuracy mean in this context?
Good question. It refers to the model's accuracy under a specific attack strength.
Okay.
So it's a measure of how well the model can withstand those adversarial perturbations.
So it's not just about general accuracy, but accuracy in the face of adversity.
Adversity, exactly.
I like it. What about computational cost? Did RRCM manage to achieve this boost in performance without sacrificing efficiency?
It did. In fact, it reduced inference costs. The time it takes to make a prediction
Right.
by a whopping 85 times compared to those other diffusion-based methods.
85 times. That's amazing.
It's huge.
Yeah, that's a really big deal.
Yeah.
Wow. What about the results on CFAR10?
Similar story there. They saw significant improvements
Okay.
in certified accuracy compared to other methods. And importantly, it achieved all of this while remaining computationally competitive
Okay.
with traditional methods that don't use diffusion models.
So they're getting the robustness of diffusion-based methods, but with the efficiency of the traditional approaches.
Absolutely, it's a win-win.
That's awesome.
Yeah, this paper really marks a significant step forward
Yeah.
in the field of certified robustness.
It sounds like it.
It's not just about incremental improvements.
Right.
It's a fundamentally new way of thinking about and achieving robustness.
This paper is clearly making waves, but, it didn't come out of nowhere, right?
Right.
There's a whole history behind this pursuit of certified robustness.
Decades of research. Remember those early adversarial examples we talked about?
The ones that could make a model misclassify an image with just a few pixels?
Yeah, with a few strategically placed pixels.
Yeah, pretty unsettling.
Absolutely. That was a wake-up call for the field.
Yeah.
It showed how fragile these models could be.
Right.
And raised concerns about their reliability, especially for things like self-driving cars.
Exactly. So
Yeah.
how did researchers initially respond to this challenge? Well, what were some of the first steps they took?
Well, a lot of early efforts focused on developing what we call empirical defenses.
Empirical defense.
Yeah, these were strategies to defend against specific types of attacks
Okay.
that researchers had already identified.
So it's kind of like a reactive approach?
It is very reactive.
Like whack-a-mole with these adversarial attacks.
Exactly. And as you can imagine, it's a never-ending battle.
Yeah, you patch one hole and another one pops up.
Exactly. And that's where the concept of certified robustness came in.
Certified robustness.
Yeah, a more proactive and rigorous approach.
Okay, so instead of just reacting to attacks,
Right.
the goal is to provide some kind of mathematical guarantee
Yeah.
that the model will withstand any attack within a certain bound.
You got a level of confidence in the model's robustness regardless of the specific attack.
And this is where randomized smoothing comes in.
Exactly. One of the most effective techniques for achieving this.
And this paper takes it to that next level
It does.
by incorporating diffusion models.
Yeah, it's really exciting to see how this field is evolving.
It is. It's really pushing the boundaries of what's possible.
It is. And it's crucial because As deep learning becomes more integrated into our lives,
Right.
the need for robustness only becomes more critical.
We need to be confident that these models will perform reliably, especially when lives are at stake.
Exactly.
Speaking of pushing boundaries, I always love to hear your novel notions,
Okay.
those intriguing ideas that kind of come to mind after reading a paper.
Yeah.
Do you have any brewing after this deep dive?
I do. One thought that keeps nagging at me is the potential of RRCM beyond image classification.
Beyond image classification. Okay, tell me more.
What if we extended this concept of representation consistency to something like video classification?
Video classification.
Yeah,
So theoretically, you could apply these principles to make video classification models more robust as well.
precisely. Think about the applications.
Yeah.
Surveillance systems, self-driving cars,
Right, content moderation.
content moderation, exactly.
All those things rely on video.
Exactly. Ensuring the robustness of those systems could have a huge impact.
Yeah, it's like this added layer of security,
Yeah.
making these systems less susceptible to manipulation or errors.
Right.
What a fascinating thought.
Oh.
Do you have any other novel notions swirling around in your brain?
I do. There's one more that I find particularly intriguing.
Okay.
What if we combined RRCM with techniques from explainable AI?
Explainable AI.
Yeah,
Trying to understand why a model makes certain decisions.
exactly. And how that relates to robustness.
I can see how that would be valuable.
Yeah, if we could visualize which parts of an image are most important for RRCM to achieve consistency,
Right.
we might gain valuable insights into how these models actually work.
It'd be like peering into the black box of AI
Exactly.
and understanding the mechanisms behind this robustness.
Exactly. And it could lead to even better, more robust models in the future.
It's like reverse engineering the secret sauce of robust AI. That would be incredible. Yeah, it's fascinating to think about how all these different areas of AI are interconnected.
It is.
Robustness, explainability, even video processing, it highlights just how dynamic this field really is.
And as we delve deeper into these areas, we're not only solving problems, but also opening up new avenues for exploration.
Yeah, it feels like every new discovery leads to like a dozen more questions,
Yeah.
each more intriguing than the last.
It's true. That's the beauty of research.
Yeah.
Speaking of intriguing questions,
Yeah.
I have one final novel notion.
Yeah, hit me.
And this one goes beyond the visual realm altogether.
Oh, I'm intrigued.
The success of RRCM really hinges on that structured noise schedule
All right.
of diffusion models.
Mhm.
And it makes you wonder, could we apply this concept of structured noise to other areas of machine learning, like reinforcement learning?
Reinforcement learning, that's where like an agent learns through trial and error,
Exactly.
interacting with an environment and getting rewards and stuff.
Exactly. Now imagine an agent trying to learn to navigate a complex environment.
Okay.
What if, instead of just throwing it into the deep end, we could introduce a structured noise schedule
Okay.
that gradually increases the complexity of the environment?
So kind of like starting it off with training wheels in a simplified world
Exactly.
and slowly ramping up the difficulty, just like adding noise to an image.
Precisely.
I like that.
It might allow the agent to learn more effectively
Okay.
and potentially discover more robust strategies.
Training wheels for AI. That's awesome.
I like it.
Who knows? This idea of structured noise might become a fundamental tool for making all sorts of machine learning models more robust.
It's definitely an intriguing avenue for future research.
Yeah.
Of course, these novel notions are just that, notions.
Right.
But sometimes the most groundbreaking ideas emerge from these what seem like outlandish thought experiments.
Absolutely. That's what makes this field so captivating.
It is.
It's this constant process of exploration, pushing boundaries, and always asking, what if?
Exactly.
And I think on that note, we've reached the end of our deep dive for today.
Indeed, a big thank you to all of our listeners for joining us on this exploration of robust representation consistency model via contrastive denoising.
It's been a fascinating journey. Be sure to check out the show notes for a link to the paper.
Yes.
And subscribe to Talk Tensors for more deep dives into the world of cutting-edge ML research.
Until next time.
Until next time, keep those novel notions flowing.